Heaviest black hole merger, Flouts, a forbidden gap. Unbelievable cosmic collision. In a discovery that challenges everything we thought we knew about black hole formation, astronomers have recorded the most massive black hole merger to date, a cosmic event that defies conventional science. Detected in November 2023 by the LIGO observatories in the United States and analyzed by the International LVK collaboration, which brings together researchers from the US, Europe, and Japan. This merger involved two titanic black holes, weighing in at approximately 103 and 137 times the mass of our Sun. Their union produced a final behemoth weighing around 225 solar masses. But here's where it gets controversial. One of these merging black holes falls squarely into the so-called mass gap, a range between roughly 60 and 130 solar masses that standard stellar collapse theory insists should be impossible. This gap is expected because stars with masses near 200 solar masses are theorized to become unstable. When their cores produce electron-positron pairs, the critical internal pressure drops precipitously, triggering a catastrophic implosion rather than forming a black hole. Since the first gravitational wave detection in 2015, the LVK collaboration has documented about 300 black hole mergers. Most of these have involved black holes around 10 solar masses, sizes that comfortably align with our understanding of how massive stars exhaust their fuel and collapse under gravity. However, this new event, known as GW2-31123, not only features far heftier black holes, but also implies that some of these cosmic giants might arise through a multi-merger or hierarchical process. In this scenario, earlier generations of black hole mergers produce increasingly massive remnants, which then go on to merge with other heavyweight objects. Imagine a family tree of black holes, each generation building upon the last in a grand cosmic assembly line. Yet, the detection of GW2-31123 comes with its own set of challenges. The gravitational wave signal, primarily in a low-frequency range, was exceptionally brief, lasting only about 1/5 of a second, making it more difficult for scientists to extract detailed information about the merger's properties such as mass, orbital orientation, and distance. Researchers had to lean on complex waveform models to derive their conclusions, inevitably introducing larger margins of uncertainty. Despite these hurdles, the best fit analysis indicates that we are indeed witnessing a merger involving objects that defy conventional mass expectations. This discovery has stirred up considerable debate among astrophysicists. For example, Davide Gerosa, an astrophysicist at the University of Milano-Bicocca, notes that the existence of black holes far exceeding 30 solar masses was a surprise even a decade ago, and now objects over 100 solar masses are challenging our models entirely. A particularly intriguing aspect of this event is the near maximal spin observed in both merging black holes, values recorded at roughly 80% and 90% of their theoretical maximum. High spin rates like these are often seen as hints that the objects might have been involved in previous merger events, supporting the hierarchical merger hypothesis. However, some experts find these numbers puzzling because theoretical models typically predict lower spins, around 70%. Could it be that additional complexities in our models or interpretations are at work? Alternative theories have also been floated. One possibility is that a massive star might merge with another star, sidestepping the parent stability process altogether. Yet, such models struggle to explain why we observe the exceptionally high spin values in this case. Another angle, proposed by theorists like Rosalba Perna from Stony Brook University, suggests that GW2-31123 may have occurred in a densely populated region, perhaps within the tumultuous disks of active galactic nuclei, where frequent interactions and a rich supply of surrounding material allow black holes to grow through successive mergers. And this is the part most people miss. With each new observation, the cosmic narrative of black hole formation becomes even more layered and complex. What exactly triggers these hierarchical mergers, and in what environments do they most often occur? Are we on the brink of rewriting the rules of astrophysics? Or do these extreme events hint at still unknown physical processes. As we continue to push the boundaries of our observational techniques, the discussion is bound to heat up. What do you think? Are hierarchical mergers the key to these forbidden giants? Or is there an entirely different mechanism at play? Share your thoughts and join the debate in the comments below. LIGO's extreme black hole merger, breaking Einstein's rules. A black hole collision of epic proportions has left scientists in awe, challenging our understanding of the universe and even pushing the limits of Einstein's theories. This groundbreaking discovery, made by the LIGO-Virgo-KAGRA observatories, involved two black holes, each over 100 times more massive than our Sun, merging to create a single, rapidly spinning cosmic giant over 225 times the Sun's mass. But here's where it gets controversial. Not only does this event break previous size records, but it also suggests these black holes may have formed in a way that current models struggle to explain. Gravitational waves, tiny ripples in space-time caused by massive cosmic events, allowed scientists to detect this record-breaking merger. These waves carry crucial information about the objects that created them, providing a unique window into the universe beyond what light alone can reveal. Black holes this massive are forbidden through standard stellar evolution models, says Professor Mark Hannum from Cardiff University. One theory is that these black holes formed through earlier mergers of smaller black holes. The high mass and rapid spinning of the black holes in this event pushed the boundaries of both detection technology and theoretical models. Analyzing the signal required advanced models that account for the complex dynamics of highly spinning black holes. It will take years for the community to fully unravel this intricate signal pattern and all its implications, states Dr. Gregorio Carullo from the University of Birmingham. Despite the most likely explanation being a black hole merger, more complex scenarios could hold the key to understanding its unexpected features. This discovery marks a new era in gravitational wave astronomy, demonstrating how much we can learn and how much more there is to uncover. As Dr. Sophie Binney from Caltech puts it, this event pushes our instrumentation and data analysis capabilities to the edge of what's currently possible. What do you think about this groundbreaking discovery? Does it challenge your understanding of the universe? Or do you have your own theories about the origin of these massive black holes? Let us know in the comments below. We'd love to hear your thoughts on this cosmic mystery. Most massive black hole collision ever recorded, GW 231123 gravitational wave detection. Imagine witnessing the universe's most colossal cosmic dance, a collision between two black holes, each heavier than 100 suns. This isn't just any celestial event. It's the biggest black hole merger ever recorded, challenging everything we thought we knew about these cosmic giants. But here's where it gets controversial. The black holes involved in this collision are not only incredibly massive, but also spinning at near-light speeds, defying our current understanding of how they form. A team of astronomers, using the Laser Interferometer Gravitational-Wave Observatory, LIGO, spotted this phenomenon, named GW231123. LIGO consists of two identical detectors, one in Livingston, Louisiana, and another in Hanford, Washington. These detectors are so sensitive that they can pick up the faintest ripples in space-time caused by such monumental collisions. Gravitational waves, as physicists call these ripples, were once considered too elusive to detect, thanks to Albert Einstein's predictions in 1915. It took nearly a century, until 2016, for LIGO to confirm their existence, marking another triumph for Einstein's theory of relativity. Following this groundbreaking discovery, LIGO and its partners, Virgo in Italy and KAGRA in Japan, had detected over 300 black hole mergers. According to Mark Hannum, head of the Gravity Exploration Institute at Cardiff University and a member of the LIGO scientific collaboration, these instruments are the most precise measuring tools ever built by humans, allowing us to observe the universe's most extreme phenomena through the tiniest of signals. GW231123 stands out not only for its sheer size, but also for the peculiarities of the black holes involved. Charlie Hoy, a research fellow at the University of Portsmouth and part of the LIGO collaboration, points out that these black holes exist in a mass range where scientists previously believed they couldn't form from collapsing stars. Moreover, they're spinning at what seems to be their maximum possible speed, posing a significant puzzle for astrophysicists. The mystery deepens with the concept of a mass gap, a theoretical range between 60 and 130 solar masses where black holes were thought to be impossible. If the black holes from GW231-123 fit within this gap, they likely didn't originate from stellar collapses but through a series of mergers. This idea, proposed by Hannum and his team in a recent study, suggests the existence of an intermediate population of black holes that don't quite fit into our current models. Another intriguing aspect of GW231-123 is the rapid rotation of the black holes. Most black holes detected via gravitational waves spin relatively slowly, making the high-speed rotation of these particular black holes even more perplexing. This could indicate a different formation mechanism or simply suggest that our current models need refinement. Dan Wilkins, a research scientist at Stanford University's Kavli Institute for Particle Astrophysics and Cosmology, emphasizes the importance of gravitational wave astronomy in unveiling new aspects of black hole populations. Unlike traditional telescopes that rely on light, gravitational waves reveal black holes that are not actively consuming matter, providing a fresh perspective on these enigmatic cosmic entities. This discovery not only pushes the boundaries of our knowledge about black hole formation, but also highlights the rapid progress of gravitational wave astronomy. As Imre Bartis, an associate professor at the University of Florida, notes, we've moved from initial detections to challenging established theories in less than a decade. Future observations, possibly with more advanced instruments like the Cosmic Explorer and the Einstein telescope, could uncover even more massive mergers, further expanding our understanding of the universe's most extreme phenomena. So what does this all mean? Are these black holes the result of multiple mergers, or something else entirely? As Zoltan Hyman, a professor at the Institute of Science and Technology Austria, suggests, while the merger theory seems promising, future detections will reveal whether GW231-123 is an isolated incident or part of a larger, more complex pattern. What do you think? Share your thoughts, and let's explore the cosmos together.